Recording.
Okay. Good morning. It's a pleasure for me to present Professor Maicon Correa from University of Campina in Brazil. Professor Maicon Correa talk today about numerical scheme for elliptic, parabolic, and hyperbolic PDEs in porous media flow. Please, Professor Correa, you can start now.
Thank you, Mauricio. Thank you, Juan, Anna, everyone for the invitation, this kind of invitation. I'm really happy to be here. Actually, my first talk in these seminars was exactly 4 years ago. So it's a huge pleasure to come back in this special edition. So thank you very much. Thank you all the colleagues, Sandra, everyone that's organized, that's been organizing this series of seminars, so interesting seminars for so long. It's a huge success. So in this talk, I will talk a little bit about the application of some numerical schemes. I said here for elliptic, parabolic, and hyperbolic PDEs, but I will put everything in context. This is a huge topic. It's not possible to talk about all the things I wanted. So this is a nice collaboration that I have with my colleague Márcio Morad from NCC. And the idea here is, since I don't know the audience, if everyone is knows well the equations that governs the flow in porous media, I will start with the most well-known equation for fluid flow, that's the Navier-Stokes. So if you wanna just simulate some fluid flow, general fluid flow, the first approach is go to the Navier-Stokes. This is the most known model for simulating fluid flow. In this case, we take a Newtonian fluid, an incompressible Newtonian fluid, and you have the equations for the first equation, 1A, is the equation for the balance of linear momentum of a Newtonian fluid, and the second equation is the mass balance. Since we assume the fluid is incompressible, the second equation is really simple. It's just the divergence of the velocity zero. Just to say here, rho is the density, u is the fluid velocity, and u is the viscosity of the fluid. And d here is the symmetric part of the gradient of the velocity. So this is a nonlinear equation, and in general, when you go for applications, it's pretty common to see some variations of this equation. For example, I just put here a picture of a river, and it's really common. In this case, we use simplifications or variations, such as the shallow water equations in 2D, or the 7A equations, for modeling channel flow, 1D equations. It's really challenging equations to solve the 7A equations. In our talk here, we are interested in another simplification of Navier-Stokes, that's just the Stokes flow. So what does it mean? It means that we are assuming the same incompressible Newtonian fluid, but now the flow is low, and we are in steady state. In other words, we are neglecting the inertial and the advective effects. So with these assumptions, we have here the Stokes problem, the problem with the simplified equation for the balance of the linear momentum, this 2A, and again, the same equation for the mass balance, the divergence of the velocity zero. This is also known as incompressibility constraints. So this is the Stokes flow, and now we move for single phase flow. Up to here, we are just in the fluid domain. We have only fluid. Now we are moving for the porous media flow. So we have here the porous medium, and we pick a point here and zoom in this point. This is nice because when you model porous media, now the mathematical point has dimension. So what does it mean? It means that now we have a representative elementary volume, and there in this volume, lots of things happen. So here we are trying to represent the fluid flow between the voids. The voids are here the pores of the porous medium. So we can assume we have one single phase flowing there in the porous medium, and this flow is low, and the fluid is Newtonian. So we can try to solve this problem by using Stokes equation in the porous domain. So here's the illustration. We have here the domain of, we zoomed in, we have the domain of the porous media, we have the voids, the pores, and inside the pores we have Stokes flow. Okay, is this a good approach? Yeah, we call it the micro scale. If you try to solve in this micro scale, we have a huge problem. We need to know the microstructure. We need to know the geometry of the grains of the porous medium, everything. And it's really hard to know that. And if you try to solve, for example, a problem in a reservoir, petroleum reservoir, or groundwater flow in huge dimensions, talking about meters, kilometers, it's impossible to do that. It's unfeasible. So this approach using the Stokes equations there in the micro, it can be done, but just for a really particular case. It's even worse when we consider not only one fluid. If we consider, for example, in this picture here, the existence of other phase. In this case, we have blue here, it's like the water phase, and the white one is the air or gas phase. So this is a real challenge. So we don't solve in this scale. We need to upscale. And if we use some, for example, average or homogenization technique, and bring this information from the micro scale to the macroscopic scale, we have, again, assuming single phase flow, we have Stokes there. And in the macro now, we find an average velocity. This is the equation also known as Darcy law, that relates this average velocity, that's the average velocity of the fluid there inside the pores, it relates the velocity with the gradient of the pressure. So this is much more simple than the solving the Navier-Stokes equation. Okay, it's good. But for the first time, it appears something new here. That's the K. K is the permeability of the porous medium. So now we have information that comes from the geometry of the pores, something that comes from the porous medium. In this case, it may be highly heterogeneous. So it's something new. It's just different. We are skipping, we don't need that first and hard equation for the linear, the balance of linear momentum of the Navier-Stokes or the Stokes is simplified. But again, we are bringing some new information here. Okay. And what happens when we go now for the case of multi-phase flow? So that equation, the Darcy law, it is valid for a single phase flow. And now we are considering something here new. We are putting lots of phase. So for us here, alpha, it represents the flowing phase. For example, we can have water, oil, gas, lots of different phase flowing. And some new quantities appear. That's nice because these quantities, they only make sense in the representation of porous media flow. We don't have that in Navier-Stokes. For example, the first one is the porosity. The porosity is the fraction between the volume of the pores and the total volume of this representative elementary volume. So this is a new amount. So you pick a point there in the domain, and you have this function, that's the porosity, that says the amount of voids that you have there in that point. As I said, now the point has a physical meaning. And another important quantity, so it's important to highlight here, the porosity, it can't be zero, because if the porosity is zero, you don't have pores, you have only like a rock without pores, and we only have solid. And if it's one, means that we are going back to the fluid flow, the Navier-Stokes. So it's between 0 and 1. And now we have the phase saturation. The phase saturation is the fraction of the volume of the phase inside the pores. So it can be 0 because, for example, if the saturation of water is 0, it means that we don't have water there. And it can be 1. If the saturation of water is 1, we have only water. So this is the context here. And this constraint here is really important, the volume constraint. So if you sum all the saturations, it's 1. From the modeling mathematical point of view, it's okay. But from the numerics, when you go to the numerics, it sometimes is really hard to satisfy this constraint. So, and the Darcy velocity, what happens? Okay, it's a generalization of the Darcy velocity. The new part here is now you have one velocity for each phase. You have different velocities for the phases. And you have the viscosity, and now you have the pressure. The pressure may be different between the phases. And you also have here a new function that we call it the relative permeability. This relative permeability brings nonlinearity to the problem because it's a function of the saturation. It somehow accounts for the difficulty or when you have other phases in presence, how the phase you are studying is going to flow. So the presence of other phase affects how the phase alpha is flowing. So this is a really important function that is nonlinear because it depends on the saturation. Okay. After that, I think it was a long introduction, but I think it's always good to talk about the modeling of porous media flow. And I explained why we are doing this kind of modeling with these average equations. And what I'm going to present now is the use. First, we are going to pick a model, a really complex model. It's a model for the black oil flow in porous media, but incorporating the geomechanical coupling. It means that the porous media can be changing in time. It's deformable. And how this set of coupled equations, coupled partial differential equations is difficult to solve, and how to introduce a numerical methodology that's kind of splitting the equations, and then just briefly talk about the choice for the numerical schemes to solve each one of these problems. So this is the idea. And another motivation, now we are talking about, for example, applications of these methodologies. And one really nice application is the modeling, for example, of the pre-salt, the Brazilian pre-salt, where we have here in this small part is the reservoir, and it contains oil when we want to extract the oil from here, this part, but it's trapped in rocks, different formations with different laws. They're deep in the ocean. So if you want to solve this problem, it's really hard to solve this huge coupled problem. So it's interesting to split the problems. For example, if I want to solve the mechanical problem, how everything is changing, the stress is distributing, I can solve the whole domain here with all the rocks, including the reservoir there. But if I'm interested in this flow, for example, where we have flow that we are extracting is just this small part. So I can solve the equations for the flow only in this small part. That's not small at all, it's huge, but we are representing here a reservoir. But the idea is, okay, I'm not solving the equation for the flows everywhere because we don't have flow everywhere. So we split the problems and we set different boundary conditions, different equations, and iterate between them to have the solution of this huge problem. That's one really nice application. So in this talk, I'm only talking about this small part here that I said it's not small at all. So the focus is on the reservoir. So we have here some simplifying hypotheses again. One important hypothesis here is that the reservoir, the solid part, behaves as an elastic solid. So the equation for the deformations of the reservoir, they are linear elastic. And we have three phases. What are the phases? The phases are water, oil, and gas. But we also have three components. The components are it's different from the phase. The phases are flowing, and you can have components inside different phases. For example, we can have gas trapped in the water. So the water is flowing, and you have gas there. The same, you can have gas in the oil. So the components are these concentrations that we are trying to track around the flow. So we have three components, the water, again, oil, and gas. But the important thing in this model is that the gas can be dissolved in oil. Okay, so you have three phases, but the component gas may be present in the oil phase and also in the gas phase. And again, another really important simplification here is we assume all the pressures are the same. So we don't have capillary effects here. We are not accounting for the capillary effects. Okay, going forward. These are the mass balance equations for the three components. And something really different from the divergence of velocity zero that we have there in Navier-Stokes. Now here we have a really set of three coupled equations that they are the mass balance for each of the components. And the first one is the mass balance for the water, and the second for the oil. And the third one is a little bit different because, as I said, you have gas, and the gas is also inside the oil. So here we introduce another really nonlinear and important function, that's the gas-oil ratio, or the gas solubility, that accounts for the amount of gas that you have trapped in the oil. So we had the Darcy law, okay, Darcy law is there, but now we have the mass balance. So the idea, okay, this form of representing the mass balance, it's a form that depends on the saturations. And sometimes it's not the best way because why? Because sometimes when you increase the pressure in this kind of model, the gas is dissolving the oil. And if the pressure is high enough, all the gas becomes dissolved in the oil. And suddenly the gas phase disappears. So if it disappears, you lose track of this part that's really important. So the idea here is this illustration of that. We have the pressure dependent data, and this last one here shows how you increase the pressure, you are increasing the dissolution, the gas is dissolving in the oil till the point you don't have gas anymore, and this function becomes constant. So this point here is where the gas disappears. It's called the bubble point pressure. So this is the pressure where all the gas becomes dissolved. And you may have different bubble point pressures, and this is really non-linear problem. So since we are not going to use the saturations, because the saturation of gas is not, we can't trust, it disappears sometimes. We are rephrasing the equations in terms of the component concentrations. So this is the form of the mass balance we are considering, because with this set of equations, we always have the concentration of gas. The saturation of gas may disappear, but the concentration is never zero. So more details on this modeling, please, I suggest you to ask me for the preprint. I don't have the link here, but we submitted, it's more than 1 year in revision, so all the details on the modeling is here. Okay, and for geomechanics, again, the solid is deforming. And then we assume here the extension of a total stress tensor. In this total stress tensor is split in the effective stress that's acting in the porous medial skeleton, and the poro pressure. So this is pretty well known in geomechanics. And the idea here is that the effective stress is ruled by this linear elastic law. Okay, and the final ingredient of this modeling is the consideration of the porosity, because it's really different in this case, since everything is changing, is deforming. Even if you start with a homogeneous porosity, because if it's evolving, the porosity becomes heterogeneous. So it's a function of space and time. And here are the composition. We are using the representation of the Lagrangian porosity. Good. I think I used almost all my time to talk about the model, but here is the model. If you want to solve this problem, you have to solve this set of coupled nonlinear partial differential equations. So it goes without saying, it's hard. It's hard to solve everything and coupled in this way. Here we have the flow problem in blue. This W here is the total flow. It's like the total velocity. And here we have the phi, the Lagrangian porosity, the concentrations, and the total stress. Everything is here. So what is the idea? The idea is to use a sequential formulation. The first version of this sequential formulation is published in this paper. And the idea is to split the problem, the whole problem, sub-problems. So we have here a subsystem for the flow, a subsystem for the transport, and a subsystem for the geomechanics. What are, mathematically speaking, we have here a nonlinear parabolic problem. The flow subsystem is a nonlinear parabolic problem. The transport subsystem is a nonlinear hyperbolic problem. It's a hyperbolic system of three equations coupled in nonlinear. And the poromechanic subsystem is an elliptic problem. So instead of solving that nonlinear coupled set of equations, we split equations and solve them independently, but using information from the previous steps. So this is the idea of the fixed stress algorithm. First, we solve for the flow, then we solve for the transport, and we iterate here to convergence. But we are not solving for the whole time, it's just for one time step. We are solving in one iteration, flow, transport, and iterate in one time step to convergence. Once they converge, we go to the geomechanics and solve the equilibrium equation for the mechanics in the whole domain. After that, we need to come back with the new displacement, new porosity, everything that's updated here, you need to come back. And this is the idea of the fixed stress. You need to iterate to conversions. It's expensive, but it's good because you may have good methods for specific methods for each one of these problems. Let me check my time here. I think. Please, Mauricio, if my time is approaching to the end, just tell me that I finish. Good. So talking about the numerical methods, that's the title of this talk. So it's not the formulation is not tied to a specific numerical method. So I'm just showing you our choice. So for the flow, we are using a Newton method based on a mixed hybrid finite element formulation. Okay. For the transport problems, a semi-discrete central point scheme. This is a new scheme. It's not known in the literature because here we need to develop this kind of finite volume scheme in the presence of the heterogeneous Lagrangian porosity. So lots of things change. So it's a pretty new scheme. It's really interesting. And for the geomechanics, it's again a mixed method posed in terms of the displacement and the spherical part of the effective stress. I will briefly show you the methods. So for the flow problem, so we are trying to solve this equation coupled with the Darcy law, the generalized Darcy law. So we integrate in time the total mass balance and have this formulation here, this multiplied by a test function. In our variational formulation, we take the V, that's the space for the velocity, is the HG, and the Q, that's the space for the pressure, is L2. So we have this nonlinear mixed form for the flow problem. It's discrete in time and continuous in space. So the next step is just linearize. It's nonlinear because of the dependence of this function here on the pressure. So we linearize the pressure with a small perturbation around the iteration P in n plus 1, the time n plus 1, iteration k. We perturbate the solution, linearize, and we have here a new variational formulation for the linearized problem. And then here are the bilinear and the linear forms. And then we finally go to the total discrete formulation that now we discretize in space by selecting the lowest order Javier-Tomei space. So this is a finite element method, well known in the literature. It's pretty robust and efficient methodology to solve this kind of problem. So here we are adopting the not the dual mixed formulation, but the hybridized variation of this formulation, where we introduce also a Lagrange multiplier. So in the end, we need to solve this linear problem as one iteration of Newton's method. So if you have there a code for the Javier-Tomei code for linear problem, you can use this in this as this form here. You can use this as part of a Newton solver, where you solve this linear problem as one iteration of Newton's method. Good. For the transport, as I said, we needed to develop a new central point scheme. We just rewrite the transport system. I don't have time to go into the details, but here's some historic evolution of these schemes. So the starting point is this method from Kurganov, Noel, Petrova. And then in 2013, we proposed a variation that is able to solve for heterogeneous porosity fields. And then after that, we moved to not this original Kurganov method, but for a variation that it's also contemplating system of conservation's law. Finally, we performed the variation of the central wind for the case where the porosity is changing in space and time. So this here is the idea. We need to interpolate the porosity, just the interpolated porosity, and evaluate some local propagation speeds. And then go to the central wind scheme. That's pretty simple. And then the final form is pretty simple. You have local fluxes, and you need to evaluate these local fluxes. They depend on the velocities, they depend on the porosities, they depend on the information of the concentrations. And if you just update these fluxes, you have in the end a system of ODEs, and you can integrate in time using your preferred method. Here we use the Hungekuta method, but in the end, the formulation is pretty simple, but it's powerful. It's a powerful formulation for the transport. And finally, for the geomechanics. The geomechanics, as I said, we decompose the stress into parts. This part here we call the spherical part, and it's related to the divergence of the displacement. And we use here a mixed finite formulation for the geomechanics that is posed in terms of the displacement. Here is not velocity, U is not velocity anymore, it's the displacement. This formulation is posed in terms of the displacement is in H1, and the volumetric mean stress is piecewise constant. So the displacements bilinear functions, and then the displacement are piecewise constant. This formulation is also really nice. It's locally conservative, and if you do everything okay, in the end you can statically eliminate the unknowns for the mean stress and solve your problem just in terms of the displacement. It's a pretty nice formulation. Okay, so for just summarizing, we are using a fixed stress algorithm. To do so, we need to solve for the flow. The flow, we are using the mixed hybrid finite element formulation with the Javier-Tomà that composes a solver for a Newton solver for the flow problem. For the transport, we are using the central wind modified to contemplate the heterogeneous porosity, and for the geomechanic, using this mixed formulation for displacement. It's really nice set, but you can choose different methods for each of these sub-problems. So the important part here is the algorithm, the idea of decomposing the equations and iterating them. But the methods, it's like, for example, for the flow, can I use just the classical Galerkin H1 formulation in terms of the pressure? No, you can't. It's really bad. The flux that we evaluate with this formulation is really bad. It's not locally conservative. It's not a good idea. Can you use finite volume formulation? Maybe you can. So depends on the quality of the methods. This set of methods that I present here, they are really good. They combine pretty well. If I have time, I will show some numerical experiment just to show the solution. We have different solutions, different problems. So this is the pressure-dependent data. I will not take long here, but this is really nice. So we are solving a slab geometry. It's kind of this two-dimensional problem. And the idea is that you don't have flow in the top part, you don't have flow in the bottom part. Here in the beginning, you inject flow. For example, you inject water, you have here inside oil. So you are injecting water and you are producing producing oil in this part of the domain. Since we have here the geomechanics, there is also a distributed load that's represented all the layers above the reservoir, the weight of the layers above the reservoir. There's this load, and you also have heterogeneous Young modulus here. So you have some blocks of heterogeneity, of permeability, and Young modulus, and these are the solutions for these three. First is the pressure. So we start with the pressurized system, and you have primary production till the day 100. So here you prescribe the pressure is 10 megapascal, and you are just producing oil by depressurizing the system. And after in 100 days, you start injecting water. And so the pressure rises again in this part. This is where you are injecting. So this is the solution. And here is the profile for the saturation of water. See, here in 100, you start injecting water, and this is the solution for the water. And this is one solution that I want to show you, that is the solution for the gas. As I said, you start with the high pressure, you are depressurizing. Since you are depressurizing, the gas that's trapped in the oil is released. So you start creating gas everywhere because the pressure is dropping. But after you start injecting water, the pressure raises again, and that saturation of gas goes to zero. So the gas phase disappears. So that's why we are not solving for saturation and solving for the concentration. These are the solutions for the concentrations. You can trust the solutions. The solutions for concentrations, they are never zero. That's why. So in the end, these are the solutions for the porosity. It's really nice to see how the porosity changes in time. So the porosity is also important point here, because even if you start with a homogeneous porosity, after some time it becomes heterogeneous. Here is the displacement. And if you go to a highly heterogeneous media, just to show you the difference, if you choose, for example, the first order version of the central upwind that we presented. We have in the paper the first order and also the second order. So it's really interesting to use a higher order approximation for the transport problem. You see here, you can see much more sharp solution. The solution here is kind of diffusive. You lose information about, for example, the formation of this finger here. Good. So this is the idea. I hope I used well the time to show you this really. Okay, I'm back. So I think I'm done here. It's good.
Okay, thank you very much, Professor Correa. There is some questions. Now it's open the audio for the question. Some question. Professor Correa, I have a question. Is you describe the transport equation in with some kind of finite volume method or the conservation law, but you describe in I see that you describe in one dimension your scheme, but your presentation is in two dimension. Is how you apply the
yes. We start with one dimension and show that you can use the dimensional split and assume that flux holds for each dimension, and use the one-dimensional approach to emulate a problem in 3 dimensions. But the most important thing here is this flux is along an edge between 2 elements. So in general, if you have a really general mesh, you are always taking the flux in the normal direction. So you can think of this direction x, that's their one dimension. Actually, in more general case, it becomes the direction of the normal flux. See, so it's easily extended to more general dimensions.
Okay, thank you. Thank you very much. There is other questions? Then we thank Professor Correa again, and thank you very much for your presentation. Very
Thank
nice
you.
picture, and very
Thank